Elizabeth looked archly and turned away. Her resistance had not injured her with the gentleman.
Ah, Pride and Prejudice. I didn't take you for a Jane Austen fan, but it's a strong opening.
It's a classic for a reason.
Yeah.
But I'm not bringing it up to discuss, the romance. I want to look at the mechanics of that second sentence. Her resistance had not injured her. As a human, you instantly know that her refers to Elizabeth.
Right, it's instantaneous. You don't even have to think about it.
But if you feed that sentence into a computer, especially like an older model,
Yeah.
it doesn't see a person. It sees a variable. And connecting that variable, her, back to the entity Elizabeth,
Yeah.
that's arguably one of the most frustrating and complex problems in natural language processing.
It really is one of the holy grail problems. You're talking about anaphora resolution.
Exactly. And that's what we're doing today, a deep dive into the mind of the machine. We're working from a really comprehensive text on this, specifically Chapter 30 of the Handbook of Computational Linguistics, which was written by the researcher Ruslan Mitkov. It's titled Anaphora and Co-reference Resolution.
It's a fantastic source. I mean, Mitkov does a great job of bridging that gap between the old school, very rule-based linguistics and the modern black box of AI.
And that's our mission. We're going to unpack why simple words like he, she, and it can cause computers to just, completely misunderstand. We'll look at the algorithms, how they evolved from these rigid rulebooks to so-called knowledge-poor shortcuts.
And we'll get into a really fascinating study that involves human eye tracking. It suggests our own eyeballs might hold the key to better AI.
It's a journey from pure syntax to actual meaning. Anaphora resolution sounds dry, but it's really about how we build reality in our heads.
It is.
So let's start with the foundations, because before we can teach a robot to read, we have to understand what reading even is. The source material draws this really sharp distinction between two concepts that I think most people use interchangeably: cohesion and coherence.
Yeah, you're right. In casual conversation, those are basically synonyms. You'd say, that plan isn't cohesive, or that argument isn't coherent, and you mean the same thing.
That doesn't make sense.
Exactly. But in linguistics, they are two very, very different gears in the engine.
Okay, walk me through the difference then, because I think getting this right is key to seeing why computers struggle so much.
So think of a discourse, like a brick wall. Cohesion is the mortar. It's the grammatical links that physically stick sentence A to sentence B.
Okay, so going back to the Jane Austen example, Elizabeth looked. Her resistance. The word her is the cohesive device. That's the mortar.
Exactly. It's a physical hook. It points back. If I just, deleted Elizabeth from that first sentence, the second sentence physically breaks.
The hook has nothing to hang on to.
Right. That's a failure of cohesion.
So cohesion is all surface level. It's the syntax, the glue you can actually see.
Precisely. Now, coherence, that's the architecture of the wall. It's
Yep.
the logical flow, the sense-making part. You can have sentences that are perfectly cohesive, they have all the right pronouns and connectors, but are just completely incoherent.
The source had a great example for this, the George scenarios.
Yes. Okay, so compare these two. Scenario A. George passed the exam. He scored the highest mark in the class.
Totally clear. He is George. The second sentence is a logical result of the first. It's cohesive and it's coherent.
Okay, now scenario B. George passed the exam. He enjoyed red wine.
Right. So grammatically it works. He is still George, so the mortar's there. It's cohesive.
But is it coherent?
Not really. It makes you stop and ask, wait, why are you telling me this now? It feels random, a non sequitur.
And that pause, that's your brain failing to find what's called a coherence relation. You start doing these mental gymnastics. You think, okay, did he drink the wine because he passed? Is he celebrated?
Or is it just a random fact about him? You're trying to force a connection.
You're trying to force coherence where there isn't any obvious connection. And this is the trap for AI, isn't it? A computer is really good at spotting the mortar, the cohesion. It can find the word he, but it's terrible at the architecture, the coherence.
It doesn't have that world knowledge. It doesn't know that exams and red wine don't usually have a direct causal link.
Exactly. Programming that kind of common sense is just incredibly difficult and expensive.
Okay, so let's double click on that mortar, on the cohesion, because that's really the focus of anaphora resolution. The technical term for this pointing back is anaphora.
It comes from the Greek for to carry back.
Right, and there's a cast of characters we need to define here to really understand the algorithms. We have the anaphor, the antecedent, and the referent.
It sounds more complicated than it is. Just take a simple sentence. The queen waved. She was smiling.
Okay.
She is the anaphor. That's the pointing word. The queen is the antecedent. That's the piece of text it points back to.
And the referent.
The referent is the actual flesh and blood person, the woman in Buckingham Palace.
And most of the time, all three of those things line up. She equals the queen equals the real person. That's what we call co-reference.
Correct. And in a perfect world, an AI would scan a document and build what we call a coreferential chain. It would link queen, she, her, the monarch all into one single bucket of meaning.
But, and this is where the real headache starts for programmers' language, is almost never a perfect chain. The source highlights some edge cases that honestly feel like logic puzzles designed to break a computer's brain.
Oh, you mean the identity of sense problems?
Yeah, these are fun.
The paycheck example. I had to read this section of Mitkoff's text twice to really wrap my head around it. The sentence is, "The man who gave his paycheck to his wife was wiser than the man who gave it to his mistress."
A true classic in linguistics.
So let's break it down. The anaphor is it. The antecedent grammatically is his paycheck.
Syntactically, yes. It's the nearest noun phrase that fits the grammar.
But if the computer assumes coreference, meaning identity of reference, it assumes the second man took the first man's physical check and gave it to his mistress.
Which would be theft, not to mention just bizarre.
Right. But we as humans, we know that it here doesn't mean that specific piece of paper. It means a paycheck of his own. The concept of a paycheck. Exactly. It refers to the sense of the word, not the specific reference. It's a type versus token distinction. The computer sees it pull paycheck and thinks it's the same physical token, the same object.
And teaching a machine that it can mean a different object of the same type that requires a level of abstraction that is just incredibly hard to code.
And it gets even messier with what's called indirect anaphora. This is where we skip pronouns entirely. The example is, the store had just opened, the food hall was busy.
Okay, right. There's no it or she there.
Oh.
But as a human, you know the food hall is part of the store.
Because you've been to a store. You have this internal map and ontology of a department store in your head that includes a food hall.
The computer doesn't have that. Unless you explicitly program a database of everything in the universe, which is what an ontology is, the computer just sees two sentences about two completely unrelated buildings. It misses the link.
The invisible assumption.
So we've laid out the problem. It's hard because language relies on this invisible knowledge. So let's talk solutions. How have engineers tried to tackle this over the decades? The source outlines a general three-step pipeline for most of these algorithms.
Right, and whether you're using code from the 1980s or AI from today, you're generally doing three things: identification, location, and selection.
Step 1. Identification, finding all the its and he's and she's.
Sounds easy, but it isn't. You immediately have to filter out what's called the pleonastic it.
The pleonastic it. I love that term. It sounds like a dinosaur, but it's actually just grammar clutter.
It just means empty. Think of a sentence like, "It is raining," or "It is important that we finish."
Who is it?
Nobody. It doesn't refer to the clouds or a book. It's a dummy subject because the English grammar says you can't just say, "is raining."
So if the computer tries to find an antecedent for it is raining, it's going to go on a wild goose chase.
It might look back at the previous sentence, see "the dog barked," and decide, "the dog is raining."
Which is a lovely poetic image, but functionally useless. Okay, so step 1 is filtering out the noise. Step 2 is location.
This is about defining the search scope. If I say he, the computer has to know how far back to look. Usually it's just the current sentence and maybe 2 or 3 before it. Any further back and you just have too many candidates.
And finally, step 3, selection. Picking the winner. And this is where the source distinguishes between constraints and preferences, which I found really, really helpful.
Yeah, think of constraints as laws and preferences as strategies.
Okay, so a constraint is a hard and fast rule, non-negotiable.
Right. Gender and number agreement is the big one. If the word is she, the antecedent cannot be Mr. Darcy. Mr. Darcy is masculine. She is feminine. The algorithm just kills that option immediately.
It's a hard filter. But constraints often leave you with multiple options, right? I mean, Mr. Bingley and Mr. Darcy are both he. They both survive the filter.
And that's where preferences come in. These are soft rules or heuristics. The biggest one is recency. We tend to refer to the person or thing we just mentioned.
Another big one the source mentions was syntactic parallelism.
It's a fancy term for a simple human habit. If the antecedent was the subject of the last sentence, the anaphor is probably the subject of this sentence. For example, John hit Bob because he was angry.
He could be Bob.
It could be. But the computer bets on John because John and he are both in the driver's seat. They're both the subject of their respective clauses.
Now, looking at the history of this, there was this huge pivot in the 1990s. We moved from what the source calls full parsing to these knowledge poor approaches. Knowledge poor sounds like a downgrade.
It sounds pejorative, I know, but it was actually a pragmatic revolution. In the 80s, with systems like the Hobbes algorithm, we tried to full parse. That means the computer would try to perfectly diagram the entire sentence, noun phrase, verb phrase, subordinate clause, before it even looked at the pronouns.
Like we did in high school English class, but on steroids.
Exactly. But English grammar is messy. If the parser made one little mistake, say, it misidentified a verb as a noun, the whole tree collapsed. It was slow, computationally expensive, and just incredibly brittle.
So people like Mitkov said, let's dumb it down, or maybe let's strip it down.
They said, let's be efficient. Instead of a perfect grammatical tree, let's just tag the parts of speech. Noun, verb, adjective. Then we apply those constraints and preferences we just talked about.
And it turned out
It turned out that a knowledge-poor system that just plays the odds using recency and gender and so on was way faster and almost as accurate as those really expensive deep parsing systems.
almost as accurate is the key phrase there, though, because the source drops a bit of a reality check. For a long, long time, the success rate for these algorithms was just stuck.
Stuck at about 60%.
That's bad. That's barely better than a coin flip if you have two candidates.
It was a very humbling realization for the field. It basically proved that syntax alone isn't enough. You can have all the grammatical rules in the world, but without that world knowledge, without knowing that monkeys eat bananas and not the other way around, you just hit a glass ceiling.
Which brings us to the modern era. We aren't really writing rules by hand anymore.
No, not since about 2015. Deep learning has completely taken over. So instead of telling the computer subject refers to subject, we feed it 1 billion words and let a neural network figure out the patterns on its own.
And it builds those vector representations.
Right. It turns words into coordinates on this huge multidimensional map. King and prince end up close together. Man and woman have a specific mathematical relationship. The model just kind of intuits these connections based on proximity.
But Mitkov's research didn't just stop at deep learning. He did something really creative, which is detailed in the source. He brought humans back into the loop, or more specifically, their eyeballs.
This is my favorite part of the whole text. They used eye tracking technology.
So they literally watched people read.
They tracked the gaze. When you read a sentence and you hit a word like it, your eye doesn't just keep moving forward. It makes a tiny microscopic jump backwards. It flicks back to the antecedent to confirm the link.
And you do this completely unconsciously.
Totally unconsciously. But that flick takes time. The duration of that gaze, how long your eye rests on the antecedent, tells you how hard your brain is working to make that connection.
So they fed that gaze data into the AI.
Yes. They essentially trained the model using the human cognitive process as one of the features. And, well, surprise accuracy went up.
That makes so much sense. It's like letting the student cheat off the teacher's answer key. You're just showing the computer where the human looks.
But here's the twist. The study also compared this fancy new deep learning method against the old school knowledge poor rules we just talked about.
Yeah.
And they found that if you optimize the weights of those old rules, if you tune them just right, they are still incredibly competitive with the new methods.
So the 1990s approach isn't dead.
Not at all. Far from it. Deep learning is incredibly powerful, but it's a black box. You don't always know why it makes a decision. The old rules, recency, subjecthood, they capture fundamental linguistic truths. It suggests that while we need new tech, the linguistic foundation we built 30 years ago was actually really solid.
So we have all this tech, neural networks, eye tracking, but the listener might be sitting there asking, so what? I mean, why does it really matter if my computer confuses a monkey with a banana?
It matters because we're trusting these systems with really high-stakes communication, and the monkey example is the perfect illustration of how this completely breaks machine translation.
This is the classic Winograd schema problem. I love this because it's so simple, but it's just so destructive to translation software.
It is. Okay, let's look at 3 sentences.
The monkey ate the banana because it was hungry.
Okay, it is the monkey.
Sentence 2. The monkey ate the banana because it was ripe.
It is the banana.
And sentence 3. The monkey ate the banana because it was tea time.
It is just the situation, an abstract concept.
Right. In English, it works for all 3. We just rely on context. But if you try to translate that into, say, German or French.
Where objects have gender.
Exactly. In German, Monkey is masculine, they're aphes, so you'd use er. But banana is feminine, the banan, so you'd use si.
So if the computer doesn't know who is hungry versus what is ripe.
It picks the wrong pronoun. You could translate sentence 2 as the monkey ate the banana because the monkey was ripe.
Which is just nonsense.
And that is a direct failure of anaphora resolution. You cannot translate accurately if you don't understand the underlying relationships in the world. Google Translate has gotten way better at this, but it still stumbles on these kinds of ambiguous cases all the time.
And it also impacts how we digest information, right? I mean, we all want AI to summarize long reports for us. Read this 50-page PDF and tell me what's important.
Exactly. But think about it. If a document mentions the CEO, then Mrs. Johnson, and then she, and the AI thinks those are 3 different people, how can it possibly calculate who is important?
It dilutes her influence. It thinks the summary is about 3 minor characters instead of 1 major one.
Yeah, and the source actually puts a number on this. It mentions a critical threshold of 80%. You need at least 80% accuracy in anaphora resolution before it even starts to help a summarization system. Below that, the errors just add more noise than they're worth.
And are we there yet? Are we past 80%?
We are crossing that line now with the latest big models like GPT-4 for general text. But for specific domains or, complex, nuanced literature, we are definitely still chasing that perfection. That last gap between 80% and 99% is the hardest to close.
It's just fascinating. We started with Jane Austen, we looked at the grammar glue, went through these paycheck logic puzzles, and ended up with neural networks that are literally watching our eyes move.
It really hammers home that language isn't just code. It's a web of pointers to the real world.
And it turns out that pointing, just the simple act of saying, look at that, is a cognitive superpower.
It is. We take it for granted, but we are constantly resolving ambiguity based on our understanding of context, physics, social cues, all in milliseconds.
Before we wrap up, I want to leave you with a thought from that identity of sense discussion. We're trying to teach computers that his paycheck and it can be conceptually the same, even if they aren't physically the same object.
It's that leap from syntax to concept.
So if a machine can truly master that, if it can understand the idea of a paycheck separate from the physical object, are we just teaching it to process language, or are we teaching it to simulate a world?
That is the ultimate question, isn't it? If you can track a referent through all the chaos of language, you aren't just reading, you're starting to understand.
A heavy thought to end on. I want to encourage you as you go about your day to just notice the word it. Notice every time you use it and think about how much work your brain just did, completely invisibly, to make sense of it all.
And maybe have a little sympathy for the algorithms trying to keep up.
Exactly. Thanks for diving in with us.
My pleasure, as always.
We'll see you next time on The Deep Dive.